Welcome to week 2. This week we're going to cover a lot of ground, covering the transport and network layers. For those of you who were in class 475, we're not going to cover all the material, but we're going to cover the key points just as a review. I will have additional background material available in the additional materials section of this week's learning module. But we're going to cover a lot of ground this week, probably equivalent to what we covered in depth in about 4 or 5 weeks in the 475 class. Like I said, our goal here is to basically review key concepts. So when we start talking about wireless networks or multimedia, or we get into the depths of cloud computing and cybersecurity, everybody is on board with all the basics. So we're going to cover, I'm going to start off with the transport layer. So talk about what we're going to cover here. So we're going to talk about different principles. We're going to talk about multiplexing and demultiplexing, reliable data transfer, flow control, and congestion control specifically, and how they relate to the transport layer protocols, mainly UDP and TCP. So going back to this diagram, just like the diagram we used in when we talked about the application layer, basically the way to look at it, going from end station to end station, this example is a server talking to a client. At the transport layer at one host is communicating with the transport layer at the other host. It's basically doing the handoff. And this, from the sender's point of view, getting data from the application layer, sending it through the other layers, and then receiving at the other end, and providing different services, or maybe very few services, depending if you're using TCP or UDP. So, we talked a little bit about in the application layer lecture of the different reasons of why you want to use TCP versus UDP. So we're already familiar with that. So because of the type of data and the reliability that we need for TCP, TCP has mechanisms for congestion control and flow control. I'm going to talk about the difference between the two of those. And also, sets up a very specific connection. And because obviously we're kind of keeping track of what's happening in case we have to resend a packet, or we have to keep track of drop packets. We have to have a connection set up. If we're using the more simple UDP, it's basically best effort, so we don't have these other mechanisms. And neither TCP nor UDP make any guarantees for delays or bandwidth. Now, when we get to multimedia, you'll see that these are going to be requirements. So this will basically either taken care of by the application layer, or sometimes they're taken care of by a middleware in between the application layer and transport layer. So let's take a look at multiplexing and demultiplexing. So basically, as we've talked about before, each process is going to use a socket to communicate from the application to the transport layer. That's basically the API that's used. And obviously, the syntax obviously varies based on programming language that you use. There might be slightly different libraries depending on the operating system that you use. But basically you have this socket API. Also, from a conceptual point of view, you could have a host, like basically most servers, that might be running multiple applications, and each application has their own socket. So because of this, you have to do some multiplexing and demultiplexing. So you have to multiplex at the sender. You have to handle data from multiple sockets and add the transport header, which we're going to use later for demultiplexing. So in this case, the sender has two distinct applications not related to each other, and they have sending things over two distinct sockets, but they're sending things out over the same through the same network stack and out the same network port. So we have to multiplex the traffic from these two applications over one link coming out of this server. Likewise, the server is going to receive data from two separate sources, and that data is going to be routed to two different sockets. So at this end, we have to demultiplex the data at the receiver so the data goes to the correct socket. So how does demultiplexing work? So basically the host is going to receive an IP datagram, and each datagram has a source IP address and destination IP address. So at the IP layer, all the IP layer is aware of is source and destination IP address. Above that, each datagram is going to carry a transport layer segment, and each segment is going to have the source and destination port number. So basically the host is going to use the IP address in the IP datagram and the port number in the transport layer segment to route the incoming data to the appropriate socket. So what happens in a connectionless demultiplexing? So if you recall from our discussion in socket programming that a created socket has a local host port number, you can see in the command for the socket a port number is specified. You'll also remember that when we create a datagram to send into a UDP socket, we specify the destination of both the IP address as well as the destination port number. So at the other end, when a host receives a UDP segment, it checks the destination port number in the segment and then directs that segment to the socket that matches that port number. So what happens from demultiplexing connectionless datagrams, IP datagrams with the same destination port number but different source IP addresses or different source port numbers are directed to the same destination socket. So you have one destination socket that is going to be serviced by hosts from multiple different IP addresses. And here we have an example. So you have an application, and it has a socket set up at 6428. And imagine this is a server, and then you have two clients, one with socket set up 5775, and one set up with 9157. So let's kind of walk through this example. Okay, so we start off with the client, sending to the server. Its source port number is 9157, and it knows to go, that its destination is port 6428. The server responds with source port 6428 and the destination port number 9157. So this particular client knows that to relate 9157 to this particular socket. And so over here, what do we have? So over here we're sending back, so the source is going to be 6428 and the destination is going to be 5775, and the opposite is going to be true, where the source port number is going to be 5775 and destination is going to be 6428. So basically you have two different hosts that are basically simultaneously using the same socket at the UDP server. All right, now let's take a look at connection-oriented demultiplexing. So a TCP socket is identified by a 4 tuple. So if you understand database theory, what we're basically saying, basically a record with 4 fields, 4 distinct fields: a source IP address, source port number, destination IP address, and destination port number. In demultiplexing, the receiver uses all 4 values to direct the segment to the appropriate socket. So the server will likely host many simultaneous TCP sockets. Each socket is going to have its own 4 tuple. So basically, each unique combination is going to have its own socket. Additionally, web servers have different sockets for each connecting client. So that means a non-persistent HTTP will actually have a different socket for each request. And so here we have the example with the connection-oriented. I'm going to kind of go through this relatively quickly, but you see every datagram and transport layer header is going to have this 4 tuple: the source IP, the port number, destination IP, and port number. And so you have, in this case, 3 different clients communicating to this server. In this particular one, you have 2 separate applications, but they're both connected to this server. Maybe this might have a file server and a web server, and this host is using both. So what you have here is, unlike the other example where you had the 2 clients are served by 1 socket, in the UDP example and the TCP example, each separate connection is going to have its own socket, even though these 2 are from the same IP address, because these are 2 separate applications with 2 different ports. Well, actually, kind of looking at this is probably an example of a HTTP connection where we're going to have separate connections for each image that we send across, or each item, a non-persistent connection. So in that non-persistent connection, we're using port 80, even though they're coming from the same location, we're going to have different sockets, and therefore an individual socket set up for each. Oops, why is it doing that to me? So my computer has a mind of its own here. So, as we can see, we have 3 segments. They're all destined to the IP address, and the IP address and the destination port numbers are demultiplexed to different sockets. So that's the big difference between connection-oriented and connectionless. Okay, so I lost the mouse there for a second. Okay, next let's take a look at UDP. Oops. Okay, so as we mentioned previously, UDP, which is defined in RFC 768, is a no-frills, bare-bones Internet Transport Protocol. It's basically a best effort service. Segments can be lost and delivered out of order to the application. So basically, UDP is used when we don't care if we lose a packet, or we don't care if things arrive out of order. It might be something that we're just, receiving something at some time sequence, and we can just drop something that's out of order, or we have an application that's able to reorder the packets for us. It's very efficient. There's no extra overhead because there's no handshaking between the sender and the receiver, and each UDP segment is handled independently of others. So, as we mentioned previously, UDP is used in things like streaming multimedia. It's very loss tolerant, domain name system, and simple network management protocol. So if you need to have a reliable transfer over UDP, the best thing to do is add reliability at the application layer and set up for application-specific error recovery. And we're going to see that a little more when we actually get into talking about multimedia, where we do some things at the application layer, or maybe more appropriately via middleware. So we're going to see some examples of this in our Wireshark lab of what the UDP segment looks like. Basically, the UDP segment has a source port number, a destination port number, a length, the length in bytes of the entire segment, including this header, and then finally payload. So why is there UDP? It's more efficient. There's no connection establishment, which can add delay. It's simple. There's no connection state at the sender. The receiver has a smaller header size. And there's no congestion control because we don't care if we drop packets. So UDP can blast away as fast as desired. So definitely certain times where using UDP is indeed desirable. Okay, let's talk a little bit about, we're kind of skipping ahead a little bit here. Oops. And we're going to skip talking about some of the mechanisms for reliable data transfer. We're going to focus specifically on TCP as we go forward. But before we do, we'll talk a little bit about pipelining. We need to understand pipelining to better understand how TCP takes care of congestion control and flow control. So you have in this first situation where the sender is a great distance away from the receiver. The sender sends a data packet and then waits for an acknowledgement, then sends another data packet. This is called a stop and wait protocol. So in a stop and wait protocol, which is very inefficient for a long distance connection, because you're going to have a very long round trip time. You basically just send one packet at a time and wait for that acknowledgement to come back. Another way to address that is to do pipeline. So in pipelining, you send X amount of data packets and you receive X amount of acknowledgements back. And then you have to keep track of your acknowledgements to make sure all your packets get acknowledged, they all get acknowledged in the correct order, and you have to make some sort of determination of whether or not you need to resend any packets if any packets get lost. So there's two generic forms of pipeline protocols: go back N and selective repeat.